Welcome to section 2.4 of MATH336. And today we're going to be talking about mechanical vibrations. So we've already discussed this a little bit in section 2.1. We were looking at this mass spring system with an extra like shock absorber. So this is like a shock absorber here, which is often also referred to as a dash pot. And this is the device that's going to provide a damping effect on oscillations in the system. So it's like a shock absorber. So you can think of it that way. So this mass is connected to this spring. And when the spring is stretched this way, then it will pull the mass back that way. Or if the spring is compressed this way, then it will push the mass this way. And this dash pot will provide a force that depends on the velocity of the object. So if the mass is moving quickly one direction or another, this will provide a force in the opposite direction to sort of stabilize it. Okay, so this is kind of the simplest example of a physical system that experiences mechanical vibrations. And this is really the starting point for people who are in this area to understand how buildings or bridges react to vibrations such as earthquakes or wind or foot traffic or whatever. So we've already seen this equation from section 2.1, so I won't go over it in too much detail again, but it does come from Newton's law. So you just basically add up all the forces on this mass. So there's a force from the spring, there's a force from this shock absorber, and there's also an external force, right? So there may be some external force that's like pushing and pulling this object back and forth. And when you apply Newton's law, that tells you that mass times acceleration is equal to the force. So we end up getting this equation here. And as long as everything here are constants, then we're looking at a linear differential equation with constant coefficients. Okay, and the x here is going to represent the displacement from the equilibrium. So that's what this x is. So it's a positive x if it's pushed to the right, and it's negative if the mass is pushed to the left from equilibrium. All right. So a couple of important notions is if we don't have any external forces, then we refer to this as free motion. And if there's no damping or shock absorber, or I mean, this is even saying that there's zero friction. So friction is a type of a shock absorber or a damping, has a damping effect. So eventually, just due to friction, this mass will not, oscillate forever because of friction. So this is saying that there's no friction, and in that case, we're talking about undamped motion. So we're expecting that in the case of undamped motion that the motion will just go forever, and in the case with damped motion, it eventually will settle down, and as t goes to infinity, this x of t will go to 0. It'll eventually settle back into its equilibrium position. Okay, so the simplest case that we have for this mechanical vibrations is going to be the free undamped motion. So we'll start there. And in this section, we're only going to be looking at free motion, because so far from the previous section, we only know how to solve equations like this that are homogeneous, where the right-hand side is 0. And so in this section, that corresponds to free motion. So we're just going to look at free motion, which will give us a homogeneous equation, which we know how to solve. In the next section, we'll look at how to solve non-homogeneous equations. And in the following section, then, let's see, that will be 2.6. So 2 sections from now, we'll return to this where we'll look at what happens when we have an external force. Okay, but right now we're just going to be looking at free motion. So 2 cases today. We'll first look at undamped motion, and then after we've done undamped motion, then we'll look at free damped motion. Okay, so if we're looking at the undamped motion case, remember that means that this C term is 0. So this differential equation will just have this mass term, and we'll have the spring term, but will not have this damping term in the differential equation. So here's a differential equation, and we immediately look at this and say, well, if these are constants and this is a homogeneous equation, so we know how to solve this. What do? We just write down the characteristic equation. So we replace the x double prime with r squared. And if there was an x prime, but we don't have one because it's undamped, then we would replace the x prime with r. And finally, we replace the x with r to the 0, which is just 1. So we put 1 there. So this is our characteristic equation, and we just simply need to solve it for r. And it's pretty easy to see that we would move this k to this side, and then we would get a negative k, and we would divide by m. So on the right-hand side, we'll get negative k over m. Let me just write this down. Maybe I'll put it over here. I'll use this. So we'll have, solving that equation, we would have, the first step would be r squared is negative k divided by m. So I think that's pretty easy to see. And then we would take the square root of both sides. So maybe I'll just do it in a couple steps here, so it's perfectly clear. So move the k over, then divide by m, and then take the square root of both sides. And we get that there's 2 roots. It's going to be plus or minus I because of the negative sign. So we'll get a plus or minus I, and then we'll have the square root of k over m. And those are going to be the roots of our characteristic equation. And we know exactly what the solution is then to this differential equation. To make our lives a little bit easier, we'll refer to this rather complicated expression, we'll refer to that as omega naught. So this is not a W, this is the Greek letter omega. So omega naught is going to be the square root of k divided by m, and this is actually the circular frequency of this mechanical vibration. Circular frequency measured in radians per second, for example. Depends on what the unit of time is, but if we're measuring time in seconds, then it's radians per second. So that's what this omega is here. And later on, we'll be able to use this omega in order to measure the frequency and the period and the frequency of the vibration. Okay, so these are our roots now using omega naught, and so therefore we know exactly what the solution is. So the 2 particular solutions of that differential equation are cosine omega naught times t and sine omega naught times t. So those are 2 linearly independent solutions to the differential equation. And so we get a general solution to the differential equation by forming this linear combination of those 2 solutions. And instead of using C1 and C2, we're going to use capital A and capital B here. So it just makes things a little bit nicer notationally. So here we'll use A and B, and we'll see why in a bit. Okay, so now that we have this solution here, we would like to write it in a different form so that we can extract information from it in terms of the amplitude of the vibration and the I guess that's the main thing that we're mostly interested in. So we would like to simplify this by, instead of having like a sum of two trig functions, we want to write it as just a single trig function, and we're going to be using cosine. So it'll just be a single cosine function. And how do we get from here to here? Well, we're going to use this trig identity right here. So it says that if we have a cosine of a theta times cosine of phi, and we add sine of theta times sine of phi, then that gives us a single cosine of theta minus phi. Okay, so that's the trig identity that we're going to use. And how are we going to use it? Well, we're going to think of, well, it's a little bit in a different order, but we're going to think of, let's see, this cosine theta, that will be this omega t, cosine omega t, and the sine theta will be the sine omega naught times t. So then this a is going to be this cosine, and this b will be this sine. Well, not exactly. So I guess we do have to make one change before we can make that identification. Okay, but then after we have this written in a form like this, then we'll be able to replace this cosine sine expression with a single cosine function, and we'll get this. Okay, but the step that we need is the following. So if this was supposed to be this and this supposed to be this, well, we know that cosine squared plus sine squared equals 1, but we don't necessarily have a squared times b squared, a squared plus b squared equals 1. So how do we make that happen? Well, what we want to do is factor out this, what's going to be the amplitude of this vibration. So first we're going to factor out this c, and then we'll figure out what c is. So if we factor out c from this expression up here, so we're going to look at this, and we're going to factor out a c. So when we pull a c out, then we're going to get a over c and b over c here. And what is this c going to be? It's the one which will give us this squared plus this squared equals 1. So in order for us to have this a over c term be this cosine theta, and this b over c be the sine, cosine phi and sine phi, then in order for this to be this and for this to be this, we need that, and we're going to call that alpha, sine alpha and cosine alpha. We need this squared plus this squared equals 1. So we need to have this relationship. And then that immediately, if we solve this equation for c, we immediately get the formula for c that we need. And this will give us the amplitude of the mechanical vibration. Okay. And once we've got c, then we can substitute this value of c into here, and that will give us a formula for cosine alpha. And we'll substitute c here as well, and we'll get a formula for sine alpha, and that will define alpha. So first we'll compute c, and then we'll compute alpha. Yeah, so first c and then alpha. And I'll explain how we can use this information here to compute alpha. Okay, so now that we have this a over c term is going to be cosine alpha, and b over c is sine alpha, then we make that substitution. So there's cosine alpha, sine alpha, and then we use that trig identity, and that will let us rewrite this term here in parentheses as cosine omega t minus alpha. And that gives us our final form that we're interested in. And as I've said a number of times, this C that appears here now, this is the amplitude. So that's really good to know. Omega naught, as I've mentioned, is the circular frequency in radians per second. And then alpha is the phase angle, and that's measured in radians. So what does this mechanical vibration look like when we plot it out? So here I'm plotting time versus this displacement. So initially, imagine we're starting by stretching the spring to the right a little bit, and then giving the mass an initial velocity of like, I guess it's a negative velocity. So we're sort of stretching it to the right, and then we're giving it a push to the left, and that gets it going. And it'll travel to the left until the spring gets compressed more and more, and eventually the spring will start pushing the mass back in the opposite direction, and it'll fly off to the right, and eventually the spring will stretch to its limit, and it will pull the mass back toward equilibrium, go past it, get a compressed spring, and so on. And so this will just keep happening. The spring will compress, push the mass to the right, and then it'll be stretched out, and it'll pull the mass back left, and so on. And it'll just keep going like this forever, because we're assuming there's no damping effect, for example, from friction. Okay, so what else do we know here? So we know that C is the amplitude. So we're going to go between like minus C and plus C, minus C, plus C, and so on. So this C here is representing the magnitude of the vibration, or the amplitude. The other thing that we're interested in is what is the period of this. So what is how much time does it take to go from one peak to the other peak? So when it's the spring is completely stretched, it'll compress, and then it'll get stretched again. And how long does that take for that full period to travel? So we just need to figure out what is this time 1 and what is this time 2 that would give us this period here. So the period is going to be this T2 minus T1. And we know that at time T1, the displacement is C, and at time T2, the displacement is C. And in between, there's no other times when the x of t is equal to C. So this T1 is sort of the first time it happens, and that will be when this term that we're taking the cosine of is equal to 0. So cosine of 0 is 1, and so we get C. And the next time is when this term here will be equal to 2 pi. That's the next time that cosine returns to the value of 1 again. And so that gives us this formula for T2. We can solve those two formulas, and we get T1 is alpha over omega naught, and T2 is 2 pi plus alpha over omega naught. If you subtract T2 minus T1, then we're given this formula for the period. So it's 2 pi over omega naught. And now this sort of makes sense. Well, I guess this is like, I referred to this as the circular frequency. So it's in the denominator here. So this is giving us like a measurement of time. But then if we convert that frequency, or this period, so if we convert this period, which is cycles per second, into frequency, we would invert it. So we have the Greek letter nu here, and this is the frequency, which is 1 over the period, and that would give us omega naught divided by 2 pi hertz. Okay, so this is measured in radians per second, and then we're dividing by 2 pi radians, I guess, per cycle. And so we end up getting the number of cycles per second, which is hertz. Okay. Okay, so that's a long discussion to sort of set us up, but now we basically have everything we need in order to look at a specific example. So let's look at this example here. We have a mass of 3 kilograms. So let me write that down. So mass is 3 kilograms, and it is attached to the end of a spring that is stretched by 20 centimeters by a force of 15 newtons. Okay, so so we need to work out this. This is telling us what the spring coefficient is. So this spring, when we stretch it, let's see. So say this is stretched from here to here. This is 20 centimeters. I think we're going to be putting everything in meters though, by the looks of it. So we're going to have meters per second. So let me convert this into meters right away. So this will be 0.2 meters. So this stretching of the spring by 0.2 meters happens with a force of 15 newtons. Okay, so I guess we have to figure out what the spring coefficient is. All right. Okay, just getting a little warm, so I took off my hoodie. All right, so let's see. So the spring force that we saw from section 2.1 was given by this equation, right? So if we're to stretch the spring to the right by a force of 15 newtons, then that means that the spring is going to be providing a force of 15 newtons in the opposite direction to bring that spring back to its non-stretched position. So we'll end up getting negative 15 newtons over here, and that'll be equal to negative k. And then this displacement that we have is equal to 0.2 meters. Okay, and when we solve this for k, we end up getting 15 newtons per 0.2 meters. Okay, and that will end up being let's see, how do we think of this? That's like 5 times 15. So, because that's like dividing by 1 over 5. So multiply by 5. So 5 times 15 is 75 newtons per meter. So that's a way to measure the strength of a spring by computing how much force does it provide per meter. So it's going to provide 75 newtons of force per meter. So if we could actually stretch the spring like a full meter, then it would be pulling back at a force of 75 newtons. And if we push it a meter, if we compress it by a meter, then it will be pushing back at us with a force of 75 newtons. So that's the spring coefficient. Okay, so let's just highlight the things that we have. So there's the mass. Here is the value of k. And we know that we are doing undamped motion. And so we're going to have c is equal to 0. So I guess that's stated some. This is example number 3 from the book. Let me see how it states it. Yeah, I guess it doesn't say precisely, but this is going to be undamped motion here. So we'll also have c is equal to 0. Okay, so it's set in motion with initial position x naught. Oh, x naught is, what is x naught? X naught is 0. So x naught is 0, that's its initial position, and then it's set in motion with an initial velocity of minus 10 meters per second. So that'll be giving it a push to the left at this velocity, 10 meters per second to the left. Okay. All right, so we'll find the amplitude, the period, and then the frequency of the resulting motion. All right, so let's solve this, set up this differential equation and solve it. So we have mx double prime plus cx prime plus kx is equal to 0. Okay. And our initial velocity or initial position is 0, and our initial velocity is equal to minus 10. Okay. So we have 3x double prime plus 75x is equal to 0. So let's write out the characteristic equation. 3r squared plus 75 is equal to 0. Okay, divide both sides by 3. And then that gives us our solutions. So we get plus or minus I times 5. Okay, so there are the roots of the characteristic equation. And so therefore, we know that omega naught is equal to 5. Okay, so that's our circular frequency. So we have a circular frequency of 5 radians per second. Okay, so therefore x of t is going to be a times cosine 5t plus b times sine of 5t. All right, great. So I guess already from the omega naught, we know what the period is, so that we know the period is going to be equal to 2 pi over omega naught. So that is going to be our period seconds. And we also know what the frequency is going to be. So the frequency is going to be 1 over the period, so 5 divided by 2 pi. Okay, so, and that'll be in hertz. Okay, so maybe it'll be good to figure those out sort of approximately, but those are the exact answers there. So let's highlight those. So t is equal to this, and then the frequency is given by this. All right. Okay, so now we want to write it in that other form, so we need to first compute the value of c. Oh wait, I guess we need to use the initial conditions in order to get the a and the b first. Okay, so that's what we need to do. And before we do that, we'll need to get the derivative of x. So we'll have negative 5a sine 5t and plus 5b cosine 5t. And our initial conditions, so x naught is equal to 0, and that tells us that a times cosine of 0, which is 1, plus b times sine of 0, which is 0, is equal to 0. and then x prime of 0 is equal to minus 10. So we have negative 5a times 0 plus 5b times 1, and that is equal to minus 10. Okay, so therefore a is 0, and b is equal to minus 2. Yeah, that's it. Okay, so therefore our amplitude is going to be the square root of a squared plus b squared. So that'll be equal to the square root of 0 squared plus minus 2 squared. So that'll be the square root of 4, and that will be 2. So there's our value of c. So c is equal to 2. Okay, so therefore, x of t is equal to 2 times, let's see, so a was 0 and b was minus 2. So we'll end up getting minus, let's see, 2, and then minus 2, yeah, so b is minus 2. So let me write this out step by step here first. So maybe I'll do this in the opposite order. So let's do this afterwards. So first of all, x of t is 0 cosine 5t minus 2 sine of 5t. Okay. All right, so there that is. And I guess we also know that this alpha term that we need, so cosine alpha is going to be a over b, and sine of alpha will be, sorry, not a over b, a over c, and sine of alpha will be b over c. So this is going to be equal to 0, because a is 0. So 0 divided by 2 is 0. And then the sine alpha will be negative 2 divided by 2. So we'll get negative 1. Okay, so now we would like to figure out what this alpha is. Let me just add a page in here to give us more room. Okay, so what is this angle alpha whose cosine is 0 and whose sine is minus 1? Well, what we need to do is write out the unit circle here. Let's see. Yeah, I guess there's enough room here. So here's our unit circle. And I guess we talked about this last time. The points on this unit circle are given by cosine. Well, I guess maybe I'll use a different angle here instead of that. So I'll use theta. So this will be cosine theta, sine theta. Okay, so those are the points on the unit circle. They're indexed by cosine theta, sine theta. So cosine theta is the x-axis, and sine theta is the y. Or not the x-axis, but the x-coordinate, and the sine theta is the y-coordinate. Okay, so what is the point? So we want the point 0 minus 1. So 0, x, and then minus 1 for the y value. So that is this point right here. So here is our point cosine alpha sine alpha right there. And what is this angle? So it's this angle here from there to there. Let's see, I'll do that in a different color so you can see it better. So that gives us this point here. And that is going to be 3/4 the way around the circle. So that would be 3/4 of 2 pi, also known as 3 pi over 2. So that is the value of alpha. Okay. Yeah, that looks good. And I guess you could check that as well. Make sure that cosine of 3 pi over 2 is 0. And sine of 3 pi over 2 is minus 1. Yeah, that works. Okay. Okay, so that's our value of alpha. And so therefore, we have that x of t is going to be 2 cosine omega naught was 5, and then minus alpha, which is 3 pi over 2. So that is our final value of the final solution. Okay, so therefore the amplitude is c equals 2 meters. The period is t equals to, I think it was, which one was it? 2 pi over 5. So 2 pi over 5, and let's calculate that. Let's see. Two pi divided by 5. So that's about 1.26. So it's like 1.26 and so on seconds. And the frequency is nu 5 over 2 pi. So 5 divided by 2 pi. And that is about 0.8. So it's like 0. Well, let's write it this way. So 0.795 and so on. And that is in hertz. Okay, so it takes a little bit longer than 1 second for it to make a full, I guess, revolution in a sense. And therefore, the frequency is less than 1 cycle per second. Okay. All right. So now let's look at the second case, which is free damped motion. And so now we're going to be including this damping term, and this will make things a little bit more interesting. So now the characteristic equation that we have is this one. And if we write down the roots of the characteristic equation using the quadratic formula, then we're going to get, so just to recall what the quadratic formula is. So normally you would have like ax squared, well, let me put it with r. So it'd be like ar squared plus br plus c equals 0. So r would be minus b plus or minus the square root of b squared minus 4ac divided by 2a, right? So that's the quadratic formula. So I'm just applying that formula to this, this equation here. So I would do this c, so it'd be minus c plus or minus c squared minus 4ac, so that would be minus 4 mk, and then divided by 2m. And so that gives us our formula for the roots of the characteristic equation. Now, from the last section, we know that the thing we need to decide is, are these two roots that we get from this equation, are they real? Are they complex? And if they are real, then are they repeated? So it wouldn't be possible in this case to have repeated complex roots. So that would require a polynomial of much higher degree. So we only have really three cases to worry about. So the first is real distinct roots, and then we have real repeated roots, and then finally we have a complex pair of roots. So and this all depends on what's happening here in this square root term. So in the square root term, if this thing that we're taking the square root of was positive, then we're going to get plus or minus some positive number here. And so that would give us two distinct roots. If this term under the square root was equal to 0, then we would get plus or minus 0 here. And so that would give us a repeated root. And finally, if this thing under the square root was negative, then we would be taking the square root of a negative number, and so that would give us a pair of complex roots. Okay, so let's look at each of those three cases separately. So first of all, when this what is called the discriminant, when the discriminant is positive, then that would give us distinct real roots, R1 and R2, which are not equal to each other. And in that case, we know that e to the R1t is a solution, and e to the R2t is a solution. And so the linear combination of those two linearly independent solutions gives us our general solution for this motion. And so we notice by this solution that there's absolutely no oscillations going on here. So there's no trig functions that make an appearance here. It's just exponential functions. And notice that both of these roots have to be negative in this situation. And so we have a sum of two exponential functions, which are both going to 0 as t goes to infinity. And because there's absolutely no oscillations, we refer to this as overdamping. So overdamping provides a damping that's so strong that it will overpower the spring and eliminate all possible oscillations. So that is termed overdamping. So overdamping is given by this condition here. So you just need to once you know what your damping coefficient is, what your mass is, and what your spring coefficient is, then you know what this thing is. So you just compute that, and if it's positive, then you're in the situation where you've completely eliminated all possible oscillations, which is a good thing. For example, if an earthquake hits and the building is moved by the earthquake, then we want it to sort of return to its upright position without oscillating back and forth. So that would be a good thing to have, this type of overdamping. If we have exactly, this term is exactly 0, then that will give us one repeated root. And that repeated root would be given by this formula here. Because when we substitute 0 into this equation here, then we just get minus c divided by 2m. And that'll be a repeated root. So we'll get R1 and R2 are both minus c divided by 2m. And in that case, we'll get a couple of solutions. We'll get the, so we're going to let p be equal to this. So we'll get an e to the minus p times t. That's going to be one solution. And then to get the second solution, we know we need to multiply by the t. So the second solution will be t times e to the minus p times t. And so that'll be our second solution. And so then we form the linear combination of those two, and this gives us our general solution here. So again, what's nice about this situation is that it is, it also does not experience any oscillations. So there's no oscillations here. But the reason why it's termed critical damping is because if we're just like a little bit off, so it's really hard to be like exactly 0. So if we're like just a little bit off from being exactly 0, then we'll either move into this overdamping situation, or we'll move into the next case, which is called underdamping. So an underdamping will give us some oscillations in our mechanical vibration. So that's why this is called critical damping. So you kind of don't want to even be close to critical damping. It's better to be sort of comfortably in the overdamping area, because at critical damping, you could very easily move into the following case, underdamping. So this is the underdamping situation. That's when we have the c squared minus 4mk is negative. In that case, we're going to get a complex pair of roots. And the real component will be this minus p, the same p from here. Let me highlight this because this is kind of an important term. So there we have that term. P is c over 2m. So that'll be the real component of these roots. And then the imaginary component will be this omega 1. And omega 1 is given by this formula here. So that's our omega 1. Notice now, because this is negative, that we factored out a negative 1. And so we have 4mk minus c squared, and that'll be a positive number. So we're taking the square root of a positive number and then divided by 2m. So this is some positive number here. Okay, so we know that we get two solutions in this situation. We'll have a exponential, or e to the minus pt times cosine omega 1t. So that's one solution. And then we'll have the exponential of negative pt times, so this guy times sine of omega 1t. And that'll give us our second solution of the differential equation. So then we just form the linear combination of those two. And again, we're using a and b here so that we can easily rewrite this in a better form. Instead of having two trig functions, we'll just have one. So this is called underdamping, since the damping is not strong enough to prevent oscillations. So we are getting some oscillations here from these trig functions. And we can rewrite it as a single trig function using the formulas that we developed above. C is equal to the square root of a squared plus b squared. And then we figure out what alpha is using our unit circle to determine this angle alpha based on these two values here. And then once we have all that, then we get our final form, where we get a sort of an amplitude, although this exponential term means that the oscillations are going to go to 0. So eventually the motion will settle down into the equilibrium state again. But But in the meantime, it'll be oscillating back and forth. I guess this is the amplitude of this. So whenever this is equal to 1, then we're going to be getting this value. And when this is equal to -1, then we'll get this as the negative value. So, and this amplitude will be going to 0 as t goes to infinity. But we're going to be oscillating back and forth. Okay. So maybe it might be nice to see a bit of a picture of what this could look like. So let's see if I can just draw a quick picture of this. So imagine this is our function. Let's see, this will be like c e to the minus pt, and this is minus c e to the minus pt. Okay. So then our oscillations will sort of be going between these two. So it'll be like this. Let's do that again. Okay. So you see we're getting some oscillations, but gradually the oscillations are, the amplitude of the oscillations are going to 0. So eventually we're going to settle down. Okay. All right, so let's do one more example here. So in this case, we're going to look at the situation where we have damped motion, and then we'll also look at the corresponding undamped motion. And the parameters that we'll use are going to be a mass of 1, and then this is the damping, so 10 will be the damping coefficient, and then 125 is the spring coefficient. The initial position will be 6 to the right, and then the initial velocity will be plus 50. So we're shoving it to the right quite quickly. So here is the differential equation that we need to solve, and these are the initial conditions right there. So we'll also find, we'll find this damped motion, and then we'll also find the undamped motion. So the undamped motion is exactly the same, but now we've just eliminated this damping term, so we get this. Okay, so let's solve these two differential equations. So the first differential equation we'll start with is the x1, I guess. Yeah, let's start with x first. So let's just write that down again, so it's clear which equation we're solving. So write down the characteristic equation. Okay, so I'm just trying to think, what is the, is there a nice way to factor this? Does it factor nicely? So 125 is 5 times 25. So that's 5 cubed. Not sure. Let's just use the quadratic formula. So minus b plus or minus the square root of b squared minus 4ac. So 4 times 1 times 125. Divided by 2 times 1. Okay, so that'll be 100 minus 500. So let's see, minus 5 plus or minus the square root of 100 minus 500 divided by 2. So minus 5 plus or minus, so that'll be the square root of minus 400. 400 is 20 squared. So that'll be plus or minus I 20 divided by 2. So we'll get minus 5 plus or minus I times 10. Okay. All right. So therefore, the solution is going to be equal to e to the negative 5t times a cosine 10t plus b sine 10t. Okay. All right. So that's what that pair of complex pair of roots tells us. So it tells me that there's one solution, which is this exponential times this cosine. And then the second solution is the exponential times this sine. And I just factored out the exponential after taking the linear combination of those two. Okay, so there's our x of t. And now we want to figure out what the a and the b are. So to do that, I need to take the derivative of this. So that'll be e to the negative 5t times the derivative of the second term, which is going to be negative 10a sine 10t plus 10b cosine 10t, and then plus the derivative of the second term, which is going to be negative 5e to the negative 5t times the second term. Okay, x of 0 was 6, I believe. 6, and x prime is 50. Okay. So we'll have e to the 0 will be 1. So I'll just put 1 times a cosine of 0 is 1. And sine of 0 is 0. So we get that. And then x prime of 0 is 50. Just check that again, 50. Yeah, 50. We'll get 1 times negative 10a times 0 plus 10b times 1 minus 5 times 1 times a times 1 plus b times 0. And that is equal to 50. Okay, so already we know that a is 6. So that is good from the first equation. And then from the second equation, we're going to have 10b minus 5a is equal to 50. But I can substitute that value of 6 in, and so we'll get 10b minus 5 times 6 equals 50. So that's 30. So I'll get 10b minus 30. So I'll add that to the other side. So I get 80. And then finally, I get b is equal to 8. Okay, so there's the a value and the b value there. Okay. So now I will, I'll write down this c value. So c is going to be a squared plus b squared. And that will be equal to the square root of 36 plus 64. And that is the square root of 100. So c is the square root of 100. So c is equal to 10. Okay. So there's our C value. And then finally, we need to compute alpha. So we have, cosine alpha is A over C, and sine alpha is B over C. So cosine alpha will be 6 divided by 10, which is going to be equal to 3 over 5. And sine alpha is B over C, which is 8 over 10, and that will be 4 over 5. And I guess we could check that 3 over 5 squared plus 4 over 5 squared is equal to 9 plus 16 over 25, which is 1. So that checks out. So that's just to check that our calculation is correct. Okay, so 3 over 5 and 4 over 5. Okay, so where does that place us in the unit circle? Okay, so here's our unit circle. So 3 over 5 and 4 over 5, that'll put it somewhere in this first quadrant here. So we're going to be somewhere in here. This will be our alpha, and this will be like 3 over 5 and 4 over 5. Okay. So that means in order to compute this alpha, I guess we could, so what I'd recommend is using cosine inverse. So a good way to compute alpha is using the following rule. So alpha will be equal to, it'll either be equal to cosine inverse of A over C if we're in the top half of the complex plane. So if sine, well, the sine term. So if this B over C is positive, and if B over C, well, plus or minus or 0. So, but if B over C is negative, then that puts us down here in this portion of the unit circle. And in that case, when we do cos inverse, we would actually get an angle which is like down here instead. So we'll actually compute this angle here, but that's not the angle we want. We want this angle here, right? So in that case, we would want to do 2 pi minus cosine inverse of A over C. Okay. All right. So, but in our case, we have that this sine alpha is equal to 4 over 5, which is positive, and so therefore alpha will be the inverse cosine of 3/4. So we don't have to worry about this 2 pi minus term because we're up in the top half of this unit circle. So therefore, alpha will be cosine inverse of 3 over 5. And let's calculate that. 3 divided by 5. And that's like 0.927 and so on. Radians. That's the radians. Okay. So if you do want that in degrees, normally we don't need degrees for anything, but let's see, there's 180 degrees per pi. So I guess I'd multiply that by 180 and divide by pi. So that's like 53 degrees Okay, but normally we don't need to know the angles and degrees. Okay, so there's our alpha. So alpha is equal to this number. And now we can write our solution down. So therefore, x of t is going to be equal to c. So well, let me just write it. So it'll be c e to the negative 5t. Let me just check. Yeah, so we'll have e to the negative 5t, and then this stuff will become 10 times cosine of 10t minus alpha. Okay, so that'll be cosine of 10t minus alpha, where alpha is given by that value there. So that is our solution for the damped motion. Okay, so now let's do the undamped motion. So that was going to be u double prime plus 125 u is equal to 0. So our characteristic equation is this. And so therefore r is going to be plus or minus I, and then the square root of 125 is, that'll be 5 root 5. 5 root 5. Okay, so that gives, so now we have our solution. So our solution is u of t is equal to a cosine 5 root 5 t plus b sine 5 root 5 t. And then we'll use our initial conditions in order to determine a and b. So I'll take the derivative of this. Okay. And let's see. Okay, so our initial condition was 6. And then the initial velocity was 50. Okay, so we get a times 1 plus b times 0 is equal to 6. And so a is equal to 6. So that's a. And then negative 5 root 5 times a times 0 plus 5 root 5 times b times 1 is equal to 50. And so we get that b is equal to 50 divided by 5 root 5, which is 10 divided by root 5, which I guess we should simplify as 2 root 5. So that's our value of b. So b is equal to 2 root 5. Okay, so now we can compute c. Um, 36, and then b squared is going to be 4 times 5, which is 20. And so we'll get the square root of 56. And let's see, I can divide 56 by 4. That's 14. So that is equal to 2 root 14. Okay. I feel like I want to check this before I go any further with this one, because it's kind of a funny number. 2 root 14. Okay, that's what I have. Okay, great. Okay. So now cosine, and maybe to distinguish it from that other alpha, well, do I need to do that? I guess it doesn't matter so much. So let's call it cosine alpha is a over c, which is 6 divided by 2 root 14. So we get 3 over root 14. And sine of alpha is 2 root 5 over 2 root 14. So we end up getting the square root of 5 over 14. Okay. And we might as well check that this squared plus this squared, that should be 1. So we get 9 plus 5 over 14, and that is 1. Okay. Good. Okay, so now we have that that sine is positive, and so therefore alpha will be the inverse cos of 3 over root 14. Okay, so if that sine alpha was negative, then we would have 2 pi minus the inverse cos. But because sine is positive, we get just the inverse cos. Okay, let's calculate that. Inverse cos of 3 divided by the square root of 14, and that is 0.64, I don't know, like 0.5 and so on, radians. Okay, and just in case you're wondering, what is that in degrees? It's about 36.7 degrees. Okay. All right, so therefore, u of t is that c value. Well, let me just highlight this alpha value as well. So alpha is equal to this. Okay, so u of t is the c value, 2 root 14, times cosine of, and then this is the circular frequency, which is this this one here. Maybe I should highlight this. So there's our circular frequency. So 5 root 5, 5 root 5, t, and then minus this alpha. Maybe I should call that a different alpha so that it's not, maybe I will. So let's put alpha naught here. Okay. Alpha naught. Okay, and there's our undamped motion right there. Okay, let's see. So I guess, you know, this is just a lot of algebra, and actually I'm curious, now that we have these two solutions, it might be nice to do a plot of them to see what they look like. So let's go ahead and do a plot of these two. So I'll just set that up and I'll be right back. Okay, so here I am in Julia on my computer. So this is the Julia that I've been typing everything in to do my calculations. So there's that initial 2 pi divided by 5, for example. 5 divided by 2 pi, arc cos of 3/5, and then in degrees. And then I was just doing that because I couldn't figure that out, and so on. So here's everything. But now I can type in my functions. X of t was 10 times the exponential of minus 5t times cosine of 10t minus alpha. Okay, so it's, I'm surprised that were, I guess, alpha, is that, okay, that does give me an error. So that alpha was what? Let's see. That was the, that was the arc cos of 3/5. So yeah, alpha equals arc cos of 3 divided by 5. Okay, so now I'll just define this again just to be sure. Okay, so and if I do x of 1, then, oh, sorry, that's not what I wanted. I wanted x of 0, 6. Okay, perfect. And I guess I don't have the derivative typed in here, but we can maybe eyeball it when we plot it. So let's do using plots. And this might take a bit. So I'm just going to pause recording for a sec. All right, so loaded the plots package. And now we should be able to plot this function x. Let's do it from like 0 until 10. I don't know, 10 seconds, I guess. So we'll see what that looks like. This might take a bit. 1 sec. Okay, so there it is. It actually flattens out quite quickly, like after 1 second. So maybe I'll just plot it from 0 to 1. That might be a better look at it. Okay, that looks good. I guess I should label it too. I guess I'll say this is damped. Let's call it damped. So there's the damped motion. Okay, that looks good. I guess I could plot that other function as well. I could plot like t maps to 10 exponential of negative 5t from 0 to 1, and you can sort of see. Oops, I made a mistake. I need to put an exclamation to say I want to modify that previous plot. Yeah, so there you see how this function is sort of going like that. And I guess we should plot like the other guy as well. So I'll plot this one. Yeah, so there you see how the it's oscillating between the plus 10 exponential minus t, minus 5t, and minus 10 exponential of minus 5t. Okay, so maybe I'll blow that up so we can see that better. Okay, so that's how those two curves are telling us how the amplitude of this function is getting reduced as time goes on. And so that's the effect of damping. So when we plot the u function, we should not see this damping effect happening. So let's plot that. Let's type in that function u. So u of t is 2 square root. I'm going to type square root like this, square root 14. I think that works. Square root 14 times cosine of 5 square root 5 times t minus alpha naught. Oh wait, how do I do this? Alpha naught, like that. Okay. Oh, I didn't like something I did. Maybe I need to put multiply in here. Okay, and I do need to define that alpha naught. So alpha naught is equal to, let's see, there. So it's arc cos of 3 divided by the square root. And I'm just hitting tab here to change that into a symbol. Like that. Yeah, that's the right value. Okay. All right. So I'm going to plot that function from 0 to 1. So I'll just do a fresh plot so we can see what that looks like. Okay, so that looks pretty nice. Okay, so now I think we're in good shape to plot both of them. So you see there's no damping happening here. Okay, so let's plot both of them. So let's plot x from 0 to 1 and label that. And then we'll plot u from 0 to 1. Oops, small u from 0 to 1. And that will be undamped. Undamped. All right, let's have a look. So you see they both start out at the same position and velocity because they have the same slope at that point. But then you see the effect of damping has on the vibration. So it's still oscillating a little bit. So it oscillates back and forth, this blue one, but it gets damped, whereas the undamped version just continues to oscillate forever between those two values of 2 root 14 up here. So that's 2 root 14, and this is negative 2 root 14 there. Okay, so that's the plot. So it's good to verify that, how that looks. And that is a good place to stop. So I hope you enjoyed that. For those of you especially going into mechanical engineering, I hope this is going to be very useful for you in your careers as mechanical engineers. But I'm sure you'll learn much more advanced techniques in your engineering courses. So this is just an introduction. All right, so thanks so much for watching.